Hi, this is Miss Sec. This is a pre-recording of the live class for Tuesday, April 21st. Please note that I expect you to watch the other two pre-recorded videos before you watch this class. You need that knowledge to be able to take this class. So if you have not watched those two videos, please watch those videos before you watch this class. Okay. This is a poll for the students who take the live class. Now, today we're going to talk about how to use exponential functions in the real world. Last week we talked about how do you know if a situation is linear or exponential. But this week we're going to use that exponential knowledge to solve problems.
So far, we've already learned about linear functions as well as quadratic functions. Today, let's open up our minds to the concept of exponential functions and see what they're all about. So if we take a look at a linear function, its change is always constant. You can expect the difference between one x value at any point to be the same as any other. It will simply be the slope of the equation. So whether you're going from an x of 4 to 5, or you're going from an x of 100 to 101, the change will always be the same. In an exponential function, however, the x value is the exponent itself. An example of an exponential function would be y equals 2 to the exponent x. As you can see, if x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 4, and so on and so forth. Notice how as x increases, the increase in y itself becomes greater and greater. This is one of the key things about exponential functions in that the graph increases at an increasing rate. It's important to look at the equation of a quadratic function and look at the difference between that and our example of an exponential function. Notice how this quadratic function can equal 0 simply by making x equal to 0 in this example. However, our exponential function can never equal 0. Even if we did 2 to the exponent of negative 100, we would end up with 1 over 2 to the exponent 100, which is a very, very small number, getting very close to 0, but still never actually touching 0, since, once again, no matter how small we make the exponent, a negative exponent will simply result in a fraction with the numerator equaling to 1. And this right off the bat means that it will not ever equal to 0. We know this because a fraction only equals 0 when the numerator is a 0. Good. So we can already see differences between the two functions, and it's important that we don't confuse the two. Now, before we finish off this video, let's quickly explore a bit more about exponential functions and what they actually look like. Here's an example of a generic exponential function. Now, if a is greater than 0 and b was greater than 1, then we can expect the graph to look something like this. If a is greater than 0 and b is greater than 0 but less than 1, then the graph will look something like this. Now, if a is less than 0 and b was greater than 1, then we can expect the graph to look something like this. And finally, if a is less than 0 and b is greater than 0 but less than 1, then the graph will look something like this. Great, so that's it for our introduction to exponential function, and we encourage you to join us in our next lessons. And until next time.
Okay, so here is a real world problem that we can use our knowledge about exponential functions. This should say April. On April 1st, a fast-growing species of algae is accidentally introduced into a lake in a city park. It starts to grow and cover the surface of the lake in such a way that the area covered by the algae doubles every day. If it continues to grow unabated, the lake will be totally covered and the fish in the lake will suffocate. At the rate it is growing, this will happen on April 30th. When will the lake be covered halfway? Remember, this should say April 1st. Okay. When will the lake be covered halfway? So I did some scratch work. So I have it over here. So these are the days in April. So the lake is doubling every day. So if the lake is doubling every day, what percentage of the lake would be covered on day 29? Well, what times 2 equals 100? Well, it's 50. So 50% of the lake would be covered on day 29. So the lake will be covered halfway on day 29, on April 29th. On April 1st, a fast-growing species of algae is accidentally introduced into a lake in the city park. It starts to grow and cover the surface of the lake in such a way that the area covered by the algae doubles every day. If it continues to grow unabated, the lake will be totally covered and the fish in the lake will suffocate. At the rate it is growing, this will happen on April 30th. On April 26th, a pedestrian who walks by the lake every day warns the lake will be covered completely soon. Her friend just laughs. Why might her friend be skeptical of the warning? So we know that the lake is doubling every day. So let's go back and look at April 26th. So I have so on April 29th, there are 50. So the lake is doubling every day. So I'm going to go backwards and divide everything by 2. So 25 is on April 28th, 12.5 on the 27th, and we're looking for April 26th. So April 26th, 6.25% of the lake will be covered. 6.25% of the lake will be covered. So why did the friend laugh? Because at 6.25%, that's a very small percentage of the lake. So on April 26th, the lake is only 6.25% covered. So that's why the friend laughed, because it doesn't look like anything to worry about. Okay, now write an equation that represents the percent of surface area of the lake that covers an algae as a function of time in days that pass since the algae was introduced into the lake, if the cleanup crew does not come. So I have done the math. I went backwards. So I started with day 30th. It had said that 100% of the lake was covered. So we had gone to day 26. So I divided by 2 all the way to the first. So we're gonna consider day 1 to be like the beginning, April 1st, the beginning of time. So we're talking about when would it be covered 100. So my function is the beginning value times 2 to the x power. 2 represents the fact that it's doubling every day. So the beginning value times 2 to the 30th power. On the 30th day, it should be 100% covered if our function is correct. So the beginning value times 2 to the 30th power is as close to 100 as you can get. So that means my function is correct. Okay, I'm waiting for a YouTube video to load.
Let's do a couple of word problems dealing with exponential growth and decay. So this first problem, suppose a radioactive substance decays at a rate of 3.5% per hour. What percent of the substance is left after 6 hours? So let's make a little table here to just imagine what's going on, and then we'll try to come up with a formula for, in general, how much is left after n hours. So let's say hours that have passed by and percentage left. Percent left. So after 0 hours, what percent is left? Well, it hasn't decayed yet, so we have 100% left. After 1 hour, what's happened? Well, it decays at a rate of 3.5% per hour. So 3.5% is gone. Or another way to think about it is 0.965. Right, remember, if you take 1 minus 3.5%, or if you take 100%, minus 3.5%. This is how much we're losing every hour. That equals 96.5%. So each hour, we're going to have 96.5% of the previous hour. So in hour 1, we're going to have 96.5% of hour 0, or 0.965 times 100 times hour 0. Now what happens in hour 2? Hour 2. Well, we're going to have 96.5% of the previous hour. We will have lost 3.5%, which means that we have 96.5% of the previous hour. So it'll be 0.965 times this, times 0.965 times 100. I think you see where this is going in general. So in the first hour, we have 0.965 to the first power times 100. In the 0th hour, we have 0.965 to the 0th power. We don't see it, but there's a 1 there, times 100. In the second hour, 0.965 to the second power times 100. So in general, in the nth hour, we do this in a nice bold color, in the nth hour, we're going to have 0.965 to the nth power times 100 left of our radioactive substance. And oftentimes you'll see it written this way. You have your initial amount times your common ratio, 0.965 to the nth power. This is how much we're going to have left after n hours. Well, now we can answer the question. After 6 hours, how much are we going to have left? Well, we're going to have 100 times 0.965 to the 6th power left, and we could use a calculator to figure out what that is. Let's use our trusty calculator. So we have 100 times 0.965 to the 6th power, which is equal to 80.75. This is all in percentages, so it's 80.75% of our original substance. So 80.75%. Let's do another one of these. So we have Nadia owns a chain of fast food restaurants that operated 200 stores in 1999. In 1999. If the rate of increase is, there's a typo here, it should be 8%. The rate of increase is 8% annually. How many stores does the restaurant operate in 2007? So let's think about the same thing. In 1999, so let's say years after 1999, and let's talk about how many stores Nadia is operating, her fast food chain. So in 1999 itself is 0 years after 1999, and she is operating 200 stores. Then in 2000, which is 1 year after 1999, how many is she going to be operating? Well, she grows at the rate of 8% annually. So she'll be operating all the stores that she had before, plus 8% of the stores she had before. So 1.08 times the number of stores she had before. And you're going to see the common ratio here is 1.08. If you're growing by 8%, that's equivalent to multiplying by 1.08. Let me make that clear. 200 plus 0.08 times 200. Well, this is just 1 times 200 plus 0.08 times 200. That's 1.08 times 200. Then in 2001, 2001. What's going on? This is now 2 years after 1999. You're going to grow 8% from this number. So you're going to multiply 1.08 times that number times 1.08 times 200. I think you get the general gist. If after n years after 1999, it's going to be 1.08. Let me write it this way. It's going to be 200 times 1.08 to the nth power. After 2 years, 1.8 squared, 1 year, 1.8 to the first power, 0 years. This is the same thing as a 1 times 200, which is 1.08 to the 0th power. So they're asking us, how many stores does a restaurant operate in 2007? Well, 2007, this is 2007 is 8 years after 1999. So here n is equal to 8. So let us substitute n is equal to 8. The answer to our question will be 200 times 1.08 to the 8th power. Let's get our calculator out and calculate it. So we want to figure out 200 times 1.08 to the 8th power. To the 8th power. She's going to be operating 370 restaurants, and she'll be in the process of opening a few more.
Okay, that was a very good video to explain how we get the formula for exponential growth and exponential decay. So we're going to do a real world problem together. The population of Pittsburgh was about 12,600 in 1820. Between 1820 and 1840, the population grew exponentially, increasing by about 70% each decade. Okay, it says construct an exponential model in the form of f of x is equal to a times b to the x to represent the problem. Okay, so the first thing I want to talk to you about is it says each decade. So in this problem, we're not counting every year, we're counting every decade. So in 1820, that was year zero, decade zero. So the population was 12,600. So in year 1830, that was the first decade. So it's every 10 years. So one represents 10 years away from 1820. And 1840 is x equals 2 because that was 2 decades away from 1820. So the population was increasing by 70%. So let's talk about expressing a percentage as a decimal. So we take 70% and divide it by 100 to get 0.7. And so the growth factor is 1.7. For this reason, our function is f of x is equal to 12,600 times 1.7 to the x power. Okay, the next question is, according to your problem, what will the population be in 1825 and 1839? So let's start with our function. Our function is f of x is equal to 12,600 times 1.7 to the x power. So 1825 means 0.5 because remember, we're starting at 1820 and we're counting every 10 years. So 2025 is half of 10 years, so it's 0.5 away. So we're going to substitute 0.5 into the function. So f of 0.5 is equal to 12,600 times 1.7 to the 0.5 power. The year 1839 means that x is equal to 1.9. Remember, 1840, x was equal to 2. So 1839 means 1.9 decades away from 1820. So f of 1.9 is equal to 12,600 times 1.7 to the 1.9 power, this is the population. So then we answer the question in a sentence. The population of Pittsburgh in 1825 was this amount, and in 1839 was this amount. And we use exponential functions to solve this problem. Okay, so the students in the live class are going to play a game of 4 questions. 2 of the questions are exponential function questions. So So let's talk about the answers to this question. So a scientist began a study with a sample of 1,500 bacteria. He noticed that the number of bacteria in the sample after T days can be modeled by the equation P equals 1,500 times 5 to the T power. In this equation, what does 5 to the T power mean? So 5 to the T power 5 means that it multiplied by 5 every day. So you started with 1,500 and then it multiplied by 5 every day, and T represents the number of days. So let's look at our options. A, the number of bacteria increased by 5 bacteria per day. That's false because that is linear. The number of bacteria, so we can cross this out. The number of bacteria increased by T bacteria after 5 days. So this is not talking about 5 days, so we can cross B out. C, the number of bacteria increased by a factor each day. That sounds okay. And then D, the number of bacteria increased by a factor of T each day for 5 days. No, it's not increasing by 5 days. So the answer is C, the number of bacteria increased by a factor of 5 each day. Okay. These questions are for the live class. I would like to explain to you how the classwork works. So you have to do 2 assignments. Both assignments are due on Thursday. You have 2 days to do 2 assignments. Now I've given you a choice board again. You can do the line paper assignment. The line paper assignment is 2 assignments. It's a vocabulary assignment and a math assignment. The project counts as 2 assignments. It's a vocabulary and a math assignment. Now, most people are going to do the choice board. So the students who take the live class can do a Kahoot right after class. But the students who do the pre-recorded class, they have to do the big ideas math. I mean, not big ideas. Have to use Pearson Easy Bridge math assignment. So the vocabulary options are on Google Classroom. And if you're watching the pre-recorded class, you can do the Pearson Easy Bridge assignment if you're not doing the line paper assignment or the project. So please email me if you have any questions. At tamu.sec@pgcps.com. No, that's wrong. tamu.sec@pgcps.org. You can also reach me by asking me a question in Google Classroom. Be safe.